Hi, welcome. In today's class, we'll be discussing about few topics of Module 4. That is, first one is SR flip-flop. As the name indicates, S stands for set and R stands for reset. In case of SR flip-flop, so it is similar to the SR latch which we have already discussed. So similar to an SR latch in that S is equal to 1 gives me set operation. The Q output is set to 1. When R is equal to 1, it resets the Q output to 0. So initially in case of SR flip-flop, we know that we have three inputs, S, R and the clock, and the two outputs Q and Q bar. The essential difference is that in between the flip-flop and the latch, the major difference is the presence of clock signal. The output Q will get the output Q only when there is a clock signal which is applied there. So when S is equal to 0, R is equal to 0, so there will be a memory, that is no state change will occur there. So the previous output which was having, so it will be retained as it is, hence it is called as memory. When S is equal to 1 and R is equal to 0, Q will be set to 1 after the clock edge, and we know that when S is equal to 1, as the name indicates, it is set, so Q will be set to 1. When S is equal to 0 and R is equal to 1, then obviously R is equal to 1 here, so the output Q will be reset, that is it will be equal to 0. When S is equal to 1 and R is equal to 1, this case is not allowed, because when S is equal to 1 and R is equal to 1, Q and Q bar will be at the same state, and we know that it is not giving the basic condition where Q bar is the complement of Q. It should have the complement states, but those two will be having the same states. That is why this state is called as forbidden state or an invalid state, and hence it is not allowed to follow that. So you can see here the SR flip-flop, as we know that when the clock signal is applied at the positive edge of the clock or the negative edge of the clock, you can take it at the same time. Fine. So for the master and the slave, for the master flip-flop, that is SR flip-flop, the clock signal is the main uncomplemented form, whereas in case of the first clock pulse will be the uncomplemented clock, that is clock bar, and for the second flip-flop, that is slave flip-flop, the clock is the uncomplemented form. First one is the complemented form and second one is the uncomplemented form there. So you can observe that this flip-flop, the SR flip-flop changes the state after the rising edge of the clock, we know that, and the circuit is often referred to as the master-slave flip-flop. When the clock is equal to 0, the S and R inputs set the outputs of the master latch to the appropriate value, while the slave latch holds the previous value of Q. When clock is equal to 0, from 0 to 1, right, so then the value of P is held in the master latch and the value is transferred to the slave latch. The master latch holds the value of P while the clock is equal to 1, and hence Q does not change there. When the clock changes from 1 to 0, the Q value is latched in the slave and the master can process the new inputs. In timing diagram, initially we can see at the last, so when S is equal to 1, the Q changes to 1 at T1. Then R is equal to 1. Then Q changes to 0 at T3. Fine. And you can observe the last state. Fine. When S is equal to 1 and R is equal to 1, then obviously there will be an invalid state there. For a rising edge triggered flip-flop, the value of the input is sensed at the rising edge of the clock and the inputs can change while the clock is low. For the master-slave flip-flop, if the input change while the clock is low, the flip-flop output may be incorrect there. So for example, in the timing diagram at T4, S is equal to 1 and R is equal to 0. So P will be equal to 1. At T5, if S is equal to 0, but P does not change there. Q is equal to 1 after the rising edge of the clock itself. However, at the T5, S is equal to and R is equal to 0 there. So the state of Q should not change. That means it should act as a memory. Yes, we can solve this type of problem if we allow only the S and R inputs to change while the clock is high. Next, we'll be designing the JK flip-flop. So, in case of SR flip-flop, we have a condition that yes, if S is equal to 1 and R is equal to 1, then we are getting an invalid state. So, in order to avoid that invalid state, or in order to eliminate that forbidden state or invalid state, we are designing a JK flip flop. So you can observe here the two SR latches are connected in a master slave arrangement, except that S and R have been replaced with J and K. Here the inputs will be J and K, and the Q and Q bar will be the outputs there. And the main correction which have been done in order to avoid the forbidden status, the last flip flop, that is the slave flip flop, Q is connected to the input of the first master flip flop, and the Q bar is connected to the input of the first flip flop. That's all. That is the master flip flop. That means that the output Q and Q bar are feeding back into the input gates. So the other things will be same. If it is 0 0 0 1 1 0, all the things will be same. But in case of 1 1 condition, that is whenever S is equal to 1 and R is equal to 1, so here J is equal to 1 and K is equal to 1. So S is equal to J into Q bar into clock bar, and R is equal to K into Q into clock bar. Only one of the S and R inputs or to the first latch can be 1 at a given time. So whenever these two are used, then we can realize that whenever the J and K are 1 and 1, so at the last state, the Q will be the toggling action of the previous output. So you can observe here, fine, whenever you have 1 1 0 there, whenever the J and K are 1 and 1, the output becomes 0. But that means that though it will toggle the previous output there. Again, when J and K is equal to 1 and 1, again the previous output 0 is toggled to 1. The lab experiment, the same thing it happens, fine. So JK, you can see the output there, 0 0, it acts as a memory, 0 1, it has 0. Then if it has 1 0, it will be equal to 1, and if it has 1 1, then it toggles there. This is for your assignment. Next, we have a T flip-flop. So, it's a special type of flip-flop which will design by using a JK flip-flop. So, we know that at 1-1 condition, in case of JK flip-flop, the operation is toggling action. And this T flip-flop, where T stands for toggling action there. You can see whenever T is equal to 0, so it acts as a memory. But when T is equal to 1, whatever the output it will be there, it will be toggled or it will be inverted. Next, we have flip-flop with additional inputs. So basically, the flip-flop is often having the additional inputs which can be used to set the flip-flop to an initial state independent of the clock, and the additional inputs are clear and preset. So it is referred to as asynchronous clear and preset input because their operation does not depend on the clock. If the clear option is given, that means that it will reset all the flip-flop to 0. If the preset is given, then it will set all the flip-flop to 1. You can see here the clear and the present inputs can also be asynchronous. That is, the clear and the set operations occur on the active edge of the clock signal. It can also happen there. Often, synchronous clear or the preset will override the other synchronous inputs. For example, a D flip-flop with a synchronous clear input will clear on the active edge of the clock when the clear input is active independent of the value on D there. Yes, so D flip-flop with a clock enable. We can see here. So D flip-flop with a clock enable here. In synchronous digital systems, the flip-flops are usually driven by a common clock so that all the state change occur at the same time in response to the same clock edge, and it is called as synchronous clock pulse. When the designing such systems, we frequently encounter situation where we want some flip-flops to hold existing data even though the data input to the flip-flop may be changing. So one way to do this is to gate the clock there. So here we can see the data D flip flop there with a clock enable. This method has two problems. That is, first, the gate delay may cause the clock to drive at some flip flop at different times than the other flip flop, resulting in a loss of synchronization. The second, if the enable changes at the wrong time, then the flip flop may trigger due to the change in the enable instead of due to the change in the clock, again resulting the loss of synchronization. So rather than the gating the clock pulse, a better way is to use a flip flop with a clock enable.